Hi, let's do problem number 21. This is section 3.3, first derivative test. So here's the function. They want us to find the critical points. They want us to find the intervals where it increases and where it decreases, and then see if we can figure out if there's maximums or minimums in there. So I want to stress that you don't need to be stressed or worried about what order you do this in. You're just going to try the first thing that pops into your head. Remember what that means. Remember what the first derivative tells us. And then look kind of on the graph where it's increasing and where it's decreasing. Okay, so that's the general idea of the first derivative test. So let's start by finding critical points. So that, remember, critical point is where the function, the derivative is not defined, or the derivative is equal to 0. So let's find the derivative here. It's pretty easy. This is a polynomial. Notice also it's a polynomial. It doesn't have a y-intercept here, so we know it goes through the origin. But other than that, we don't know too much about it. But we'll differentiate it. It's pretty easy to differentiate. Polynomials always are. So 6x squared plus 6x minus 12. And to find critical points, we're going to make that equal to 0. So this is where the first derivative is equal to 0, where the slope of the tangent line is 0. It's horizontal. And look at that, and you can say, well, I can divide everything by 6 on both sides. If I do that, I get x squared plus x minus 2 equals 0. And that's going to tell us that's pretty easy to factor. That tells us where the critical points are, where the slope of the tangent line is 0. So this will be x plus 2 and x minus 1. So critical points are going to occur where x equals negative 2 or x equals positive 1. So when we do our graph, we're going to have some kind of a graph like this. We're going to have a critical point here at negative 2. So right here there's going to be a critical point. And there's also going to be a critical point at positive 1. So right here. So we're going to evaluate the first derivative in those 3 intervals created by those 2 critical points. Notice there's no place where the first derivative is not defined, so there's no, it's defined everywhere. It's a polynomial. Derivatives of polynomials are again polynomials, so that's a nice thing. So hopefully this makes sense. We're going to see what the first derivative is doing in this interval, what the first derivative is doing in this interval, and what's the first derivative doing in that interval. And we know that right here, f prime is going to equal 0. And here, f prime is going to equal 0. Right? If you put negative 2 in here to the derivative, it's equal to 0. So the slope of the tangent line at that point is equal to 0. Okay, so pick a point here in this interval. So let's pick, this is negative 1, negative 2, positive 1, right? So let's pick a point over here. Let's find f prime at negative 3. So you just pick a random point in there. That negative 3 is an easy one. Put it into this equation. Let's put it into this equation here in the original one. It doesn't really matter, but let's use the original one. So f prime at negative 3. And you can do this with your calculator if you like. It's pretty easy to do in our head, but let me do it on the calculator just because that's, I think, normally the way you do it. So it's going to be 6 times, then parentheses, negative 3, parentheses squared, plus 6 times negative 3. Minus 12. And that turns out to be 24, so that's positive 24. We don't really care about the number, we just care that it's positive over here. So the first derivative in this region right here is going to be positive. Then we'll pick a first derivative in this interval here, and the one that's always easiest there is going to be when x equals 0. So make x equal to 0, and when we do that, you can see this is really easy. We can do it in our head. It's going to be negative 12. So it's going to be negative in this region in here. And then finally pick a point over in this region, maybe at 2, and see what the first derivative does there. This is going to be 6 times 4 plus 6 times 2 is 12. So 24 plus 12 is 36. Take away 12 will be positive 24. So it's going to be positive over here. Okay? So it looks generally like our function is going like this. It's going up in this region, it's going down in this region, it's going back up in that region. And that makes perfect sense for a cubic equation, right? A cubic, this is a cubic. So we would expect that it goes, you know, something like this. So up here, down in the middle, and back up over here. Okay? Now we happen to know, you know, it's pretty, we do know that the function passes through the origin. You can tell that because there's no y-intercept. So the y-intercept is 0, so we know it goes through the origin. And now what we'll do is let's evaluate the function at these critical points. So I'll put negative 2 into the original function. So now I'm going to do this, f of negative 2 in the original function. So it'll tell us where it is at these critical points. Now, again, I'll do this on my calculator. So 2 times parentheses negative 2 cubed plus 3 times parentheses negative 2 squared minus 12 times negative 2. And that turns out to be 20. So f at negative 2 is 20. We know it's 0 right there. Let's see where it is at positive 1. Now all I have to do is change the negative 2 in my calculator to a positive 1. It's pretty easy to evaluate. So this is going to be 1, 1, 1. And that turns out to be negative 7. So this is negative 7. So now we know what the function looks like pretty much. We know it goes at negative 2, it's positive 20. So let's say this up here is positive 20. And at the origin it's 0. At 1 it's negative 7. So let's say maybe this is negative 7 here. So it looks like it goes up like this, comes down here, hits there, and goes back up. And the slope, of course, at these points here, at the critical points, are going to be 0. Okay? So that's kind of what that function looks like. So we know that these are going to be relative extrema from the first derivative test because it's negative on one side, positive on the other. We know the value there. So if you have questions about that, you know, we can go over this tomorrow. But generally, that's the strategy for using the first derivative test. Okay, thank you.